Okay, now we are going to walk through another paper here, unseen again, but this time there is um, something we need to take note first before we get started, because there is this clarification notice. So yeah, this is one of very few times that I see that there is a mistake in the paper. So they tell you here that there is a mistake in question 2. Sorry, question 1. And we're gonna have to adjust that. So this is just like a correction for the question, and that is question 1B on page 2, right? So okay, I'm just gonna get started. I'm gonna hit the timer. Okay, and now let's crack some eggs. So question 1 right here. So we're gonna just have to fix that first. So instead of the direction of a vector, that is just gonna be the one that is parallel to that vector, right? In a direction that is parallel to that vector. All right. So I'm just going to use this file to just turn to the question. And this one to just do the question. So question 1A. Find the magnitude of the acceleration of the particle. All right. So we have three forces, three force vectors, and then we have the mass of 2.5 kilograms. Well, guys, Newton's second law here, sigma F equals ma. That means we have to find the resultant force first, and that is done by adding all the forces, right? That would be our resultant force. So we have, I prefer doing a column vector like this. So we add the x component on top. That is minus 16 there for the second one and minus 2 for the third one. And the y component, 8 plus 2 plus 8, yeah? So just showing that we add them up, indeed. And what we get here is minus 12 on top. Yeah, because 6 minus 16 minus 2 is minus 12. And then down here we get 18, right? So that is in newtons. Okay, so yeah, sigma F equals m, which is 2.5. Yeah, and then A, that is the acceleration vector. So I'm just going to do A bar like this. All right. So A bar would be, just dividing across two sides by 2.5. So that's minus 12 over 2.5 and 18 over 2.5 for the acceleration vector. All right. So let's do a calculator here. Hang on, let me bring my calculator first. Okay, so minus 12 over 2.5. I got minus 4.8 here. And the other one, 18 over 2.5. I got 7.2 here. That's the acceleration vector, right? The magnitude is then a modulus A would be doing the Pythagoras in the square root here. Okay, and then we got, so 4.8 squared plus 7.2 squared. So that would be 8.6. I'm just going to do that first and then put it to two significant figures. That is usually the usual number of significant figures in this paper. Two significant figures, yeah? Okay, so that's it. Question B. Yep, a fourth force, F4, P and Q, where P is a constant, is added. So it's like a force that is kind of like 45 degrees. The resultant force of the four forces acts in the direction parallel, right? We have fixed that question now. So I just didn't put it in there, but it's in here, yeah? From the clarification notice. So we have the resultant force being parallel to that. So if we now add the new force to our resultant vector, before we had the resultant vector to be minus 12, 18. So we're not going to do everything from the start again. I'm just going to add that by PP like this, yeah? Because both of the components are P, right? And that's the new resultant vector. Okay? Now, we say that this is parallel to that vector 7, 2. So parallel means that it is a multiple of each other. So I put k as a multiple, which is unknown, and then 7, 2. We need to find this unknown so that we can get vector p. And as you can see, there are two components here. So the first component, we can make an equation minus 12 plus p equals 7k. I'm just expanding k inside. Yeah, so that's the first equation. And then the second equation is similarly 18 plus p equals 2k, right? As you can see, we got two equations. We can solve simultaneously. Yeah. Well, because we need to find p, right? I mean, but we can try subtract them. Yeah, if I do subtraction, I got minus 12 minus 18. P will go away first, but I know that we need it, but we can solve for k and then plug it in to find p later on. And 7 minus 2 would be 5k, right? So this is k equals minus 30 on the left side, divided by 5 equals minus 6. So that means p would be equal to, so let's do the second equation. So 2 times k minus 18, yeah? Okay, so that's the p-value, which is minus 12 minus 18 minus 30. That's just the p-value there. Okay, I think that's it for this one, yeah? Next question number 2. There you go. Just gonna do it here. Number 2A, sketch. Speed time graph for the motion of motorbike as it moves from A to C. Right. So there are 3 fixed points, A, B, and C in a straight line horizontal road. And okay, so from A to C first, right? Yeah, it's every point. Okay. So I'm just gonna do that. Speed is v, it's m per s, and then time is second, I think. Okay. So at time t equals 0, motorbike passes through A with a speed of 5. So it begins with some speed. So this is 5, right? Okay. And then from A, that's A. So this is A, yeah? This is point A already. The motorbike accelerates uniformly until it reaches B with the speed V. So accelerate uniformly, let's just do that because we don't have much space there. And this is probably B. And the speed is just capital V here. Okay. The motorbike takes T1 seconds to travel from A to B. So we gotta do T1 here then. Okay. From B, the motorbike decelerates uniformly until it comes to rest at C. So come to rest, that means V equals 0. Decelerate uniformly. Motorbike takes T2 seconds from B to C. Just gonna do something like this, yeah? Now takes T2 seconds from B to C. You gotta be careful because if you put T2 right here, it's gonna be wrong. It takes T2 seconds to go from there to there. So this period is T2. That means if you want to plot on the x-axis, this is not T2, it's T1 plus another T2, right? Gotta be really careful. Okay? And I guess that's it. That's it, the plot. Yeah, we got everything in. Okay. So B now, we're gonna use that graph later, I guess. The distance, here we go. The distance AB is 132 and the distance BC is 136. Okay, in terms of V, the expression for T1. So this area here, which is the travel from A to B, yeah, is 132. So the area under the VT graph is going to be the distance travel, right? So we can find this area. So this area is just a trapezium. So the height in this case, because it's on the side, right? So the height is T1 and the parallel sides would be 5 and V. So we do 1 over 2, height is T1 times 5 plus V would be equal to the area that is given to be 132. Okay? Yeah, we want to find T1 in terms of V. So we want to isolate T1 here. So I do, yeah. So we multiply 2 on the other side, we get 264. And then this would be left with T1 times 5 plus V. So we divide across by that brackets, and I'm just going to write V plus 5, which is the same. So this is T1. Just that. Okay, just that. All right. That's I. So I. We're going to do similar thing for B to C, right? Because this is, again, another triangular area. So we do half base height. So the height is still V, but the base is T2, right? Because this period alone is T2. So we have half times base T2 times height V equals the distance traveled, 136. So that means T2 would be equal to, this is 27.2, like that, divided by V, yeah? Okay. All right, so that's T2 there. So C, given that the motorbike takes 28 seconds to travel from A to C. Okay, so, previously we have computed T1 and T2. So we're just going to add T1 plus T2. That is from A to C. It's going to be equal to 28, right? And yeah, we already got T1 and T2 in terms of V. We want to find the value of V. We just substitute them as shown here. Yeah, that's it. And then we solve this equation. I'm guessing it is a quadratic, right? Because if you cross multiply, you're going to see. So if I multiply across by V plus 5 for every term, I'm going to get 264 here times V plus 5 plus 272 here times V. So 28 would have V. I'm just going to write V and then V plus 5. Yeah, like that. Okay, just multiplying across to simplify the equation so that we can solve easily. So this is, let me move a bit here. So 264V plus, okay, so 264 times 5 is 1,320. No V there. That's another V here. So this is 28V squared now. And then plus 28 times 5 is 140. 140V. All right. A little bit on the edge there. Okay. So if we rearrange for the quadratic form, I'm going to make this positive. So that means 264 plus 272, which is these two added. And then I'm going to move that to the other side. So I do minus 140, but it becomes a negative. So minus 396 V. And then this side, this will be subtracted. So I get 1320 equals 0 on the right side. Not sure if we can simplify that, but let me try. If I divide across by 28, I'm not going to get an integer there. So let me do 14. No. 7. I mean, I could put this to a calculator, but I don't have. So I couldn't have, right? Let me see. If I divide across by 2 first, I get 14V squared minus, so that's 198V minus 660. Could do another 2. So 7V squared minus 9v minus 330. So that's the quadratic equation I'm going to solve. But I might want to factorize first, so let's do that. 7v and v. Let's see. So 33 and 10. 33 and 10. No, but close. We could do 33 and 10. No, it's 11 and 30. 30 and 11. No. Interesting. Okay. I guess I gotta go the quadratic formula. I'm not sure how to factorize that manually yet. So minus b 99 plus or minus square root b squared minus 4ac, yeah? Okay, so square root 99 squared plus 28 times 330. Well, that's a horrible number. Okay, it might have to be that horrible. And then we have 99 minus, that's going to be negative, so I do plus here to get a positive. And then this has to be all divided by 2a, which is 2 times 7. So I do equal and divide that by 14. So I get 16.9. Okay, so that is my value. I'm gonna have to check back on this later, I guess. But let me do it now, actually. So start with 5 plus v. So this is fine. And the other one, yeah, still okay. Decelerate to 0. And then we add these to get 28. Right. So we multiply the cross by v times v plus 5. We get, oh no. Oh, I made a mistake. This one. This should be a v. This should be v plus 5 instead. Sorry, guys. So this is 264v plus 272v plus 272 times 5 is 1360. Okay, everything collapses here, right? But at least I found it. So this is 6 and then 536 here. I guess that's better by the looks. So the quadratic equation becomes 28v squared, 140 minus 536, which is minus 396v minus 1360. And yeah, we can try this already, yeah? So this is 396. Wait, why is it a bit different this time? No, I guess that's fine. Yeah. Okay. B squared, that's a large number. Minus 4ac. Yeah, because I didn't simplify it. That's why. 2 times 28. Yeah. Okay, so we're gonna do that. I'm guessing we gotta do plus, because if we do minus, then it's gonna give you another negative root, which is not what we want. And that is plus 4 times 28 times that divided by 2 times 28. Oh, it's an integer. Right. What's the other one, just in case? It's a negative. Okay, just gonna write that down. But we reject it. So V equals 17 meters per second. Yeah. All right then. C. Given that the motorbike takes, D, not C. Find the deceleration of the motorbike. So the deceleration of the graph along this path here, B to C. Then we can do V divided by T2, because V to 0, that's the change in speed V. And then the time is T2. So change in speed over time is deceleration. So 0 minus V over T2. Yeah. Which is minus 17 over, we haven't found T2. So we need to find T2 first. If we plug T2 is 272 over V, right? So 272 over V. All right. Okay, so that is 7 squared, if you do the fraction there, divided by 272. So that's about minus 1.0625. So deceleration equals 1.1 meter per second squared. That's it for this whole thing. Let's do the next question. Okay, looks like a momentum. Here we go. Question 3. Find lambda in terms of m. Particle P of mass 3m, 3m kg, and a particle Q of mass m are at rest on a rough horizontal surface. The distance between P and Q is 1.4 there, okay? An impulse of magnitude lambda is now applied to P in the direction PQ. Right, so the P will move to the right, I guess. Immediately after the impulse applied, the speed of P is 5. Okay. Find lambda in terms of m. Right, so we know that impulse is equal to change in momentum. So impulse of lambda, yeah, lambda being to the right direction, we convent right direction is positive, equals m of, this is mv minus u, right? Okay, so m of p is 3m kilograms, and because it was at rest at first, so the initial speed is u here, but the v is 5, right? Yeah, after the impulse is applied. So we want to find lambda in terms of m, then this would become 15m. That's the answer there. And then b, immediately before p collides with q, the speed of p is 2.5. So you see it loses some speed. Yeah, the coefficient of friction between P and the surface is mu. Find the value of mu. So you lose some speed, so you lose some energy. And the energy will be sort of like used to overcome friction because there is friction on the ground. So the kinetic energy lost will be equal to work done to overcome friction. That's energy conservation there. Okay? That's kind of too easy for this. Oh, this is M2 actually. Maybe I'm gonna use Suvat instead of energy conservation because you guys, if you haven't done M2, you might not know this. So I'm gonna use Suvat then. So P moving to the right, but there is a friction force to the left, right? So frictional force here will become resultant force because there's only force along the horizontal, and that would be put to MA to find A, right? So the frictional force is negative mu. Okay, so frictional force is usually mu r, right? But our r here, because there's no pushing, pulling across the vertical direction, that means the r would be just the mg. But the m of object P is actually 3m, right? So we do that. So this is 3 mu mg equals ma. We just want to find the deceleration here basically first. So m cancel. That means the deceleration is going to be negative 3 mu g. All right. It's negative because it's against the direction of motion. Now, we're going to put this to a deceleration for Suvat equation. That is the equations of motion. So at first it was 5, and then now it is 2.5 over some distance. The distance, hang on, let me find that. Yeah, so before it collides with Q, the distance traveled would have been 1.4. So we have a distance 1.4, we have final speed, we have initial speed, we have distance, final speed, initial speed. We want an acceleration because we know it here. So this equation doesn't have any time, so that means the most suitable equation of motion would be this. You got to practice selecting the equation from the 5, right? Because that's quite critical for M1 when you're doing Suvat, right? So V squared would be 2.5 squared. U would be 5, right? Because it was faster at first. And plus here 2, and A should be a negative. and S here should be 1.4. So if we solve for this equation, we're going to get mu. And of course, G is 9.8 in this paper. So mu would be equal to, if I rearrange everything, so it's going to be 2.5 squared minus 5 squared, isolating what I want. So this is 2 times 1.4 down here, times, this is all minus, right? 3 and 9.8. So that's going to be the value of mu. Okay, I'm just going to put everything in here. 2.5 squared minus 5 squared over minus 2 times 1.4 times 3 times 9.8. Okay, let me check everything again. I think I'm happy with that. So this is 0.227 blah blah blah. So we're just going to put two significant figures maybe. Just 0.23. Okay, that's the mu for question B. C, immediately after P collides with Q, the speed of Q is 2.1, of course, to the right. Find the speed of P immediately after collision. So we can use conservation of linear momentum. So M1U, I'm just going to do P and Q then. MPUP plus, let's move a bit to the left. So MPUP plus MQUQ equals MPVP plus MQVQ. Yeah. Total momentum before collision equals the total momentum after the collision. So MP would be 3m. So 3m UP is 2.5. Yeah. Plus MQ something, but UQ is 0, right? MP after the collision, we are finding it actually with P here. And MQ is just M. VQ, it says 2.1, so we put 2.1 here to the right direction. Okay, so this is easy then. Of course, we can cancel all the M's. So we get 7.5 on the left side, and then this is 3VP plus 2.1. So VP rearranging, we get 7.5 minus 2.1 all divided by 3, yeah? Okay, so 7.5 minus 2.1 divided by 3. So we get 1.8 meter per second. That's VP. Okay? All right, so that's done for the third question. I'm going to go ahead and do the fourth one here, which is this whole thing. Starting from this page. Okay, so a uniform rod AB has length 3 meters and weight W newtons. The rod is suspended by two light vertical ropes. Okay. One rope is attached to the rod at A and the other rope is attached to the rod at C, where AC is 2.1. Okay. Yeah. The rod is in equilibrium in a horizontal position as shown in figure 2. The tension in the rope is C equals 350 newtons. Okay, show that W equals 490. Right. So I'm just going to draw the rod as a line like this. And we are given that the tension at C, so which is a force here, upward force, is 350 newtons, yeah? So we want to show that W, which is the weight of a uniform rod, the weight of a uniform rod, which acts somewhere in the middle, right? So this is W here. And because this rod is 3 meters in length, so this would be halfway, which is 1.5 meters, yeah? Okay, so, looks like if we take moments at point A, it's going to solve for W. Usually when you do an equilibrium question in mechanics papers, from my experience, you usually start with moments. That's just my observation here. They would like you to start with moment. And this is also true in other syllabi. Like moments will do the thing first for you, and then you can use forces later if you want to find other things like the tension at A or something. But okay, let's take moment, right, at A, yeah? So that's the notation there. Okay, so we take the pivot at A, or take the moment about A. So we have 1.5 times W here, which is the clockwise moment, equals the anti-clockwise moment, which is 350 times whatever the length from A to C. So that's 2.1. So that's it really, because we don't have any other forces acting on the rod. Yeah, let me check that. No, yeah, so that's it. So we need to just show that. So W equals 350 times 2.1 or divided by 1.5. So hopefully that should be what it wants you to show, which is 490. It is 490, all right. Okay, so that's it for question A. B, a particle P of weight 210 newtons is attached to the rod at a distance D. Now, do we have something else? A distance D from A. So I'm just gonna draw that again quickly, because I can't really copy, that would be cheating. And this is electronic. Okay. Particle P of 210 attached to the rod at a distance D from A. Tension now increases to 600, so I gotta change that. So let's say maybe the particle is, let me think about that. Maybe I'm gonna put just somewhere here. I don't know yet. Maybe I'm wrong. Maybe it's further to the right, but yeah, okay. This is D, and this is 210 newtons. Okay, so it's another moment, right? Another moment. So yeah, take the moment at A again. So we have now clockwise moment being 210 times D plus 1.5 W again, which is now 490. We have proven that. And then this would be put equal to 600 times the length AC, which is 2.1, the same. Yeah. Okay. Yeah, we want to find the value of D. So D is just that minus that, just solving the equation basically, divided by 210. All right, so I'm going to put that whole thing into the equation. Fraction 600 times 2.1 minus 1.5 times 490. And down here we have divide by 210. So I get 2.5. So that is further to the right than halfway. Okay, so D is 2.5 meters. Okay. Now, on the bottom here, particle P is removed from the rod. Okay. Particle Q of weight x newtons is now attached to NB. Okay. The rod remains in equilibrium in a horizontal position and is now on the point of tilting. All right. This is very important here. So if you are on the point of tilting, that means one of the tension must be removed. Okay. So you put a particle here. You have a tension here, which is some unknown T. You have a weight here, 490, which is not changed, 1.5. Okay. So although if you imagine in reality, right, if you want to make this whole rod where it is hung by two ropes, you want to make it tilt to this direction. If you imagine the only point that is to act as a pivot would be that. Because when it tilts that way, it's going to go like that, yeah? Slightly like that. Tilt it up a little bit and down this way. So that means the tension, right? The rope at an A would become slack, meaning that there is no longer tension in that rope, meaning that we can ignore it, meaning there is now only one tension that is holding the whole rod to prevent it from falling. Yeah, so that's it. That's when on the point of tilting. So you gotta know how to deal with this kind of scenario here. We have particle Q weight X, yeah? So this is weight X, not mass. Okay, again, we will take this as a pivot. So let's take the point of hanging as a pivot. So this is NB, because we have 2.1 and 3 there, so this must be 0.9, right? And what about this? So because that is 1.5, so this is 0.6, right? Yeah, because from A to C is 2.1. So we do again, take the moment at C, right? This is point C. Take the moment at C. So clockwise, it would be 0.9x, right? 0.9 meters times x equals anti-clockwise would be 490 meters. Sorry, 490 newtons times the distance here, which is 0.6, right? Okay, and that's it, because we don't have any other forces. Okay, so x is just solving all that. Okay, so I do fraction 490 times 0.6 over 0.9. So x becomes 326.7, I guess. Yeah, so that's it. Nothing much. Just know how to deal with the point of tilting. This would be Newton, yeah. Okay. Number 5. So number 5 here we have some kind of vector question. In a game, a ball B is rolled across a horizontal surface towards a fixed target. The ball is modeled as a particle moving with constant velocity. At time t1, the position vector, okay, vectors then, position vector of B is that, and t9 position vector of B is that. Find the velocity. All right. So this is basically just suvat, but in a vector form. So v equals u plus at, but the a, the u, and the v are all vectors. So let's take the final velocity as 10 minus 3 here in a vector form, because it's 10I minus 3j meters. Wait, hang on. I got the wrong equation. Okay, let me change the equation, sorry. It's the final position vector equals the initial position vector plus v, which is a constant, times t. So v, r, and r are all vectors. So the final position vector is 10 minus 3. The initial position vector is minus 2, 5. The time here from t equals 1 to t equals 9 is 8. Right? You gotta do 9 minus 1. So I'm gonna put 9 minus 1 here. And the position vector, the velocity vector is what we want to find. So basically, velocity vector is just, 1 over 8, because I'm going to divide the other side by 1 over 8. But then before that, I do 10 minus 2 and minus 3 minus 5. Okay, so that would be doing the math there. We get 12 over 8. And then here is minus 8 over 8. Okay, so velocity vector here would be, 12 over 8 is 1.5, right? Yeah, it is. So 1.5i plus minus 1 j. That is the velocity vector in meters per second. Okay, so that's question A done. Question B. The position vector of the target is that. Use the model to find the distance of B from the target at time t equals 7. Okay. At time t equals 7. Okay. So we might want to find the location of the ball when it's at time of 7 seconds first. So at time equals 7 second, then r, which is following this equation here, equals the initial position vector. Oh, this is tricky here, because time equals 7. That means the change in time, this one would be 6. You got to be careful, because when we did this, wait, hang on. Yeah, it is as if we take time equals 1 of initial to be initial location here. And this is at time equals 1. So we can do that still, but we need to know that whatever the time is given, we need to subtract 1 from that first. So here time would be 6 instead, not 7, right? Because we start from t equals 1. And then the velocity vector is still the same. So this is 1.5 and minus 1 here. That would be the position vector at time t equals 7, yeah? So I do R7 here. So this is minus 2. 6 times 1.5 is 9, I believe. Yeah. And then 5 minus 6 here. So this is 7i minus j meters. Now, if you want to find the distance from B from the target, so we do distance of B from the target, we do square root delta x squared plus delta y squared. Yeah, that's Pythagorean or Pythagoras. So it would be equal to. So B here is 10 for the x, so we just do 10 minus 7 here, squared. Just the delta x between the B coordinates and the position vector coordinates here, yeah? Okay. And then plus y of B is minus 3, and then we subtract that by that, yeah? So that would be plus 1 squared. Okay. Just checking. Yeah, I'm happy with that. Wait. No. Hang on. Wait, sorry. Position vector of the target is 13 minus 5. Use the model to find the distance of B. Oh no. Okay, sorry. We need to use this. The B is not, sorry. Okay. I took the position vector at t equals 9 somehow. Okay, so this is 13. We gotta use this target position vector here. Minus the location at time t equals 7. Yeah. So which is 7 here. Yeah. This is R at t equals 7. So plus minus 5 minus the y of the R7, which is plus 1 here because minus minus. Okay, that's it, right? Yeah, so that should be it. So this is equal to square root of, this is 6, so 36, plus this is 4, so 16. So square root of 52, which is 7.2 meters. Yeah, I think I'm okay with that. Okay, so I'm just going to go on and do number 6 now. Okay. Particle P of mass m is held in equilibrium on a fixed rough inclined plane by a light inextensible string. The plane is inclined at an angle of alpha to the horizontal, where alpha is less than 45. We got to make note of that. The string is inclined to the plane at angle alpha, as shown in figure 3. Okay, so it's like alpha and alpha there. The string is on a greater slope of inclined plane, fine. When the tension of the string is 0.75 mg, P is on the point of moving up the plane. Good. So when it says that, we know that whatever the friction might be, it should be against that direction. So the friction should be down the slope, right? So we have here, okay, up the slope, and then particle here. This is, say, T, which is given to be 0.75 mg, right? And this is alpha here, okay? So there's of course, like an mg sine alpha here. So when you do an inclined plane, yeah, you should know that whenever you resolve the diagram, resolve the forces of weight, for example, that would be mg cos of this angle here, and this would be mg sine. You can just work out the diagram, you always get that. If the angle given is this angle and not the other one like this, which is weird. So usually this is mg sine and this is mg cos, right? So I'm just going to use that. So this angle, sorry, this direction, we also have the mg cos alpha. Okay. And yeah, so we can resolve that to be 0.75 mg cos alpha 2, and this is 0.75 mg sine alpha, right? To solve that fully. So I'm going to do resolving the tension force, right? So this is 0.75 mg cos alpha because the angle is close to the vector there. And this is 0.75 mg sine alpha, yeah? Is that everything? No, because we also have friction. So friction to the left, to down the slope, because it's at the point of moving up. So friction should be there. Now let's do equilibrium. Okay. Frictional force. Yeah. Okay, fine. So frictional force is usually mu. Do we know mu here? Does it give you mu? No, we don't care about mu yet. It's just frictional force. Okay. So we do this direction here, up, down the slope. So that would be 0. I prefer 3/4 somehow. Yeah. So 0.75 is 3/4. So I'm going to do 3/4 mg cos alpha. Do we know cos alpha? We don't know anything yet. That's fine. Cos alpha equals f plus mg sine alpha. Yeah. Basically that. And that's just the first equation. All right. In terms of mg and alpha, oh, I think we got it. So f as a subject is then mg. If I subtract this to the other side and pulling mg out, I get inside sine alpha minus 3/4 cos alpha. So that is in terms of m and g and alpha. I think that's fine. Yeah, that's it. So that's friction for A. So for B, the coefficient of friction between P and the plane is 1/2. Show that tan alpha is 2/5. Okay, so because we know that friction is equal to mu r, but r in this case is, r, I forgot to just draw the r here. So r should be up perpendicular to the plane as well. So there's another force here, r. So we know that r, if we do, let me just do the equilibrium on the perpendicular direction first. So it's 0.25 is, wait, this is 7.5, no? 3/4 mg sine alpha plus r equals mg cos alpha, right? That's just force equilibrium on the direction perpendicular to the slope. So that means we can get r by just, making it making it by itself. So isolating r. So mg cos alpha minus 3/4 mg sine alpha here. And that would be our friction. We substitute in there, basically, to find mu. All right. Yeah, and we are given that this mu is 1/2, right? And this is 1/2. So I'm just going to substitute that, 1/2. And we just expand maybe. So we expand 1/2 mg cos alpha minus 1/2 multiply in, we get 3/8 for that term, mg sine alpha. And then we will equate this to that. Just substitute the whole friction to that, right? So we do 1/2 mg cos alpha minus 3/8 mg sine alpha equals, well, gotta expand in, mg sine alpha for that first equation here we got, minus 3/4 mg cos alpha, right? And then we can do some simplification here. We can cancel the mg out. So cancel, 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 cancel. And we would collect the like terms for the sine and the cos, right? Because at the end of the day, eventually we will divide the sine by the cos, and then we get tan. So I see 3/4 here. I can move it to the other side. I have 1/2 plus 3/4 cos alpha here. And then 3 over 8 here, I move to the other side. I have 1 plus 3 over 8, and then I factor sine alpha out. So I get that. Yeah? So basically, if you want to get tan, you just do sine minus cos, over cos. So this would be 1 over 2 plus 3 over 4 divided by 1 plus 3 over 8. That would be a tan. I hope that's 2 over 5 then. Yeah, that's a half, and yeah, okay. Wait, sorry. This is 1 plus 3 over 8. Uh-oh. Doesn't look like it's 2 over 5, guys. Got something wrong here, maybe. Okay, let's double check. So, yeah, let me double check everything. So this is friction. Friction is here. Yeah, I already multiplied in. Okay, I gotta check from the beginning, maybe. So friction should be acting down, that's right. This is, yeah. We resolve this. Cos alpha, this is 0.75 mg sine alpha. This is R. So that is, this should be right. 3 over 3 mg cos alpha equals F plus mg sine alpha. Okay. Uh-oh. No, this is wrong. Oh, no. This should be the other way around. Guys, sorry. This is 3 over 4 cos alpha minus sine alpha. Bad algebra right there. Gotta be careful. So, this should be swapped. All right. So, yeah, it's still kind of, so this is minus 1 plus instead when you move this. And this will be negative instead. So I get a negative here and a negative here. So I'm just going to fix that in my calculator right here. Yeah, so I get minus. Wait, what? Is it minus? Oh, no, sorry. This is wrong. Yeah, all right. 2 over 5 as required. Phew. So C now determine whether P remains at rest. Okay, the string breaks. That means there's no longer any tension. That means we need to find if so now the object will try to go down. That means friction will be this side instead, and the only force pulling it down would be the mg sine alpha, yeah? Okay, so we need to decide which one is greater. So F here would be, again, mu times R, and R in this case would be mg cos alpha, because when you again resolve the particle on the plane here, you would have that mg cos alpha, and that is R, which they are equal in this case. So mu R is mu, the same value, half, and mg cos alpha here. Okay, what about the other value? The other value is mg sine. So we have to decide which one is greater between half mg cos alpha or mg sine alpha. Okay, this is tricky because we don't know what alpha is, but because I just spotted that it tells you that alpha is less than 45. Aha. If alpha is 45, let's say if alpha was 45, then cos and sine would be the same value, right? But if it's small, then the sine value of the angle, if it's smaller than 45, then sine would be greater than cos. You can try pick an angle less than 45 and try do that in the calculator. You'll find the sine is less than cos. Now, so here we know that sine alpha should be greater than cos alpha. Sorry, less than. All right, but we don't know how much less. But, yeah, right. Oh, but we know tan alpha, sorry. Oh, okay. So we know tan alpha. So tan alpha is 2/5. So that means we can do something like this. The trick, just draw the triangle and 2/5 right here. Sorry, 2/5 right here. Yeah. So that means this guy is square root of whatever, 4 plus 25 is 29. Okay, so we can just use these ratios in this triangle to just work out the f and the mg sine. So mg sine alpha would be mg times 2/√29. Okay, which is about 0.371 mg. But half mg cos alpha is half times cos alpha would be 5/√29, right? mg. So we do that, change that to 5. Now 5/2 times √29. So that is just 0.464 mg. I need to pick up some parcel in front of my house again. I'll be back in a minute. All right, guys, I'm back. Sorry. Okay, where were we? We found out that's basically the 1/2 mg cos alpha, which is the friction, is greater than the weight pulling it down. I mean, this is basically the maximum friction. Okay? It's not really the real friction because we calculate this by using the coefficient of static friction, and that is the greatest friction that it could get, but it doesn't mean it will get this friction. Well, actually, if the force pulling it down is less than this maximum friction, then it means the actual friction would be the same as 0.371. So this means that it's not going to go down, right? If the maximum friction, so F S max is greater than the weight component, or mg sine alpha. So we say that, so this is Fs max. So we say that P remains at rest, okay? Yeah, because maximum friction is greater. That's it, that's done, nice. Number 7, we have connected particles, dynamic here. A, find the tension in the string in terms of M and G. Okay, so one end of a light inextensible string is attached to a particle A of mass 2m. The other end is 3m. B, string passes over a smooth fixed pulley. The string taut is both straight parts and string are vertical. Both particles are held at distance 0.5 from the ground. The system is released from rest and B moves downwards, of course. Intuitively, B would move downwards and the other one move up. Okay, find the tension. So we separate them and do a separate free body diagram. So this is for A is 2m and g. This is going to be moving up, so acceleration is up. For B, T is the same because it's inextensible and smooth pulley here. 3mg. Okay, the acceleration is down. So we do for the I'm just going to do B first. So 3mg minus T equals 3ma downwards. And then the other one, T minus 2mg equals 2ma upwards. So on the right part, on the right diagram, I use A as downwards. That's why I do 3mg minus T and not the other way around, because you would subtract the pulling force minus the pulling force by the upward force, right? And the other one is the opposite. So if you subtract the two equation, add the two equation, yeah, you get mg, right? Just 1 mg here. So I'm just going to write them actually. 3mg minus 2mg, T cancel, you get here is 5ma, right? So A would become, this is 1 mg and ma, m cancel, so A is g over 5. Okay, just do the math there. Yeah, I'm happy with that. Find the tension in the string in terms of m and g. Okay, we just got A, we gotta find T. So T would be equal to 2ma plus 2mg, just from the second equation. So 2m g over 5 plus 2mg. So that is 2m, 1, 2mg. Just factorize 2mg out, and that would be 1 over 5 plus 1. So 1 over 5 plus 1 is basically 6 over 5. So that's 12 over 5 mg, right? Right? Yeah. So that's it for the tension. Okay. B. Find the speed of B at the instant it strikes the surface. So this is SUVAT, guys, because we have distance traveled to be 0.5 and we know the acceleration. So the speed is 0, the initial speed, the final speed, we don't care. Okay. We want to find where we actually do care the final speed. We find the final speed here. And the acceleration downwards would be 12, g over 5. The distance traveled is s equals 0.5, right? So that is the only one equation that should be used is this one. So v would be the square root of the right hand side. So u squared 0 plus 2a is g over 5. S is 0.5, right? Just substitute everything in. Yep. And then, yeah, we can find this as a number, right? But let's try that. Square root 2 times, should we do in g? 0.2, maybe we shouldn't. Yeah, just multiply everything. G is 9.8 times 0.1 here, because 0.5 cancel with 5, get 0.1. So that's 1.4. Okay, that's convenient. Okay, so that's the velocity when it strikes the ground. In the subsequent motion, A does not reach the pulley, and B does not rebound after it strikes the surface. So this is implying that the string becomes slack, right? Not taut anymore. That means they are no longer in a connected system, no longer connected particles, right? And we want to find the time from the instant when the system is released from rest to the instant when A first reaches a height of 1.06 meters above the surface. All right, so okay. So above the surface. Right. Okay, so imagine when B is already on the ground, right? Okay. When B is already on the ground, that's about the ground, all right? Don't mind that. Where is A? A is 1 meter from the ground, right? Because B is moving down 0.5, that means A has moved up also 0.5 from where it was. It was initially at 0.5 from the ground as well. Going up by another 0.5, you would have 1 meter from the ground. That's where A is when B strikes the surface. So we got to find an additional time from that location of A to where it wants to be. So it's 1.06 meters above the surface. That's when we want A to first reach the height of that. So we want to find a little further time here to get it to 0.06 meters, right? That's the final location of A. Okay, so but the first 0.5 meters of A motion would be still in a connected particle system, which would be the same acceleration, right? So, but then another 0.06 here would just be a different acceleration. And because there is no tension anymore after that, we say that the acceleration should be the one due to gravity. Okay, so we want to find this t here. Okay, so we need to find the initial speed of A first, which would be the same as the speed of B when it strikes the ground. So initial speed of A here, we take it as 1.4 meters per second, right? Because we just calculated it. And then we use V equals, well, that's the final question. I don't have any other pages left. Yeah. So the final speed of A when it reaches 0.6 there, we can use it, we can calculate by using S equals UT plus 1/2 AT squared. Right? So S is 0.06 equals U is 1.4, T is what we want, plus half, A is minus 9.8, T squared. So we're going to need to solve this quadratic equation, right? Okay, so what's the best way to do that? If we multiply everything by 100, no, you know what? I'm just going to use a quadratic formula there. Yeah. Just going to move everything here. Pardon me here because I'm out of space. Oh, no. Okay. So we're going to solve this quadratic equation, right? Okay. So solving that quadratic equation is just basically t equals so I'm just going to take this as a minus 0.06 on the other side. So minus b plus minus square root b squared, that's b squared, minus, I'm out of space. Okay, you know what? I'm just going to squeeze in a little bit here. Minus b plus or minus square root b squared minus 4a would be minus 4.9, right? Here. And c would be minus 0.06 if you move it to the right side. And all divided by 2 times a, which is still minus 4.9. All right, so that's my t value there. So I'm going to put everything in the calculator. I'm guessing I should do a positive here first because that would make time more likely to be positive. So that's, ooh, hang on. That's a minus there, minus 4ac. Yeah, they're all minus. 4a and c. Do I get a, yeah, I get some value there. So 2, ooh. Yeah. If I change this to a negative, I get a different value. So when it first, yeah, because we get two values when it goes up and go down, on the way up and on the way down. We should use the value of time that is less, smaller. So we have 0.233 here, one of them. And the other one, if I change that back to positive, we get 0.233. 0.525. We're gonna pick this one because it's smaller. So this is only the time after, after the particles are no longer connected and A has reached 0.06 meters above where it was, above 1 meter, right? So we haven't got the time for the first 0.5 meters in the motion yet. And that is calculated by, going back to this equation, taking all the V, the U, and the A, and the T there. Okay, so we can also do, so this T1, and this is T2 maybe. So this is T2, T2. T1 is just the first half meter. Okay, that's the initial line. So T1 is basically equals V minus U over A. We can take it from the motion of B, right? So V here was 1.4 minus U, 0, right? Over A. A was G over 5, yeah? Yeah. So that would be the first lot of time to make B go down to strike the ground. Okay, so we do 1.4 divided by 9.8, and here multiply 5. Okay, so that would be 0.7143. So all in all, T1 plus T2 equals that plus 0.0525, right? So here I have squeezing in T1 plus T2 equals 0.77 second from the ground up to the point where it reaches 1.06 meters above the surface. Yeah, it's just two different periods of time added up in the subsequent motion, guys. Okay, I hope that's fine. Yeah. So that's it for the whole 7 questions. I think I'm done. Pretty much. Yeah, I'm done with this. I'm not going to stop the timer yet. I'm just checking. So if you bear with me, I'm just going to go through all the checking process just in case. I think I'm okay with this. So let's check. Yeah, so this is adding all up. Number 1, adding all up, we get minus 12 for the X. We get 18 for the Y. We equate that to 2.5 kilograms here. So that's fine. We find the magnitude of A. I'm just going to go up here. The magnitude of acceleration, yeah. So that's 8.7 meters per second squared. This is now adding a new force, PP. Then we use the 2 equations to solve for that. We get P to be minus 30, so that's fine. Yeah, this was almost a flop, right? Luckily, I got V to be a nice number, so that is likely to be correct. And then, yeah, we got the deceleration here. So I just answer like that. This is fine, I guess. This is also fine. All right, guys, I think I'm going to stop there. So yeah, we'll mark the paper. Okay, so let's mark the paper. This is the mark scheme for IAL M1 2025 January. Let's mark the first one. Okay. Okay, so A, I got 8.7 here for the acceleration. And then this one minus 30 for the P. Okay. Number 2, I got the graph here starting from 5 and then up to V and then down to 0. All the X values are fine. I got the labels for the title axes thing. B, they asked you to give the T1 and T2 in terms of V, right? So that was fine. 2C here, 17 only. Did I get 17? Yeah. Okay, 2D, 1.1. All right, so number 2 was fine. Number 3, momentum, I think. So I did it here. A was 15. R is, wait, what? Mu is, oh, I got it wrong here, this one, guys. What happened? So yeah, I got R here, fine. Yeah, I got that mark. Then F equals mu R, that's fine. And then, what did I do? I got the acceleration to be this first. Wait, B asks you to find mu. Okay. Huh. Okay, let's see the alternative here. Did they use Suvat or something? Because I thought, so they just use sigma F equals ma here. Right, I should have used that actually, I forgot. But I don't know why this is wrong though. S is 1.4, V is 2.5, U is 5, right? Yeah. So immediately before P collides with Q, the speed is 2.5, but at first it was 5. So 5 to 2.5, yeah. A is minus 3 mu G. Yeah, I got it from there. 3 mg mu. Oh, this is 3, not m. Oh, man. Yeah. I think I lost one accuracy mark there, another accuracy mark for this, so I lost 2. Because I did this, but I didn't quite get... Yeah, I forgot to put 3m there. All right. So still got the method mark, I think. Let's see, actually. The second method mark for B. Correct method using N to L. Yeah. To give an equation in M, must have correct number of forces and either 3m or m on both sides of the equation. Right. Or on neither side, allow missing G. Okay, yeah, I think I got it. So I lost 2 marks here, sadly. And that was 1.8. Okay. Okay, 490, 2.5, 3, yeah, okay. Yeah, number 4 was fine. Number 5, 15i minus j. 7.2 or better. Okay, number 6. Where's the answer? Yeah, 0. Okay, yeah, I factorize mg out, so that would have been the right answer, yeah. Almost made a mistake for this one, actually. B, 2/5, yeah, tan theta. And then we conclude in the last part that it remains at rest, right? Because friction, maximum friction is greater than, yeah, that's the number they got. Yeah, okay. Yeah. Connected particles. Yeah, I got the equation, blah, blah, blah. And then I solve 12/5 mg for T. And then B, V is 1.4. C is, oh, that's the last question, really. 0.77. Yes, nailed it. It's just if you remember, it's just the time during which it travels a further of 0.06 meters here. All right, so let's check if I got 100 UMS. Maybe I don't. All right, so let's have a look. So bring up the Safari here. I got to change that to M1. So how many marks did I lose again? I think I lose 2 here, right? I lose 2 marks, right? Okay, so I got 73 out of 75 for that. Let's see. So, oh, that's harsh. So you need all raw marks to get 100 UMS this time. I didn't get 100 UMS. I get 96. Only just those 2 marks that I lost. I forgot to do 3M, right? It should have been 3M there. All right, guys. Yeah. Feedback. So this first question might be already tricky. You can start off losing some concentration and marks here already if you don't know what to do with the F4 here. Yeah. And when you add another F4, put it equal to some multiple of the vector that is parallel to. So this is the direction parallel to this vector. It's a multiple, which is a k multiple of that vector it's parallel to. Yeah, so beware that you have to do this and solve for the k and the p in this case that you want. The motion graph is fine. It's a bit tricky in the case where you have to solve a quadratic here. Yeah, you are required to know how to solve quadratic in M1, of course. Yeah. Number 3 is momentum. So yeah, it's the one I lost marks for. Yeah, this should have been 3M. And that should have been correct. Yeah, it was fine for this one. Yeah, okay. So this one is important. You will see quite often in this paper that when they do moments question, it's something called the limiting equilibrium. When you have now on the point of tilting. And when it's limiting equilibrium for the case when you hang something or when you put something on a two support balance system. So when it's tilted towards one end, the other support on the other side will lose contact. In the case of hanging by a string, the string will no longer apply tension, will no longer have tension to the system. So that is where you only consider one of the tensions, right? So as I said in the walkthrough, the string on this end will become slack, right? So slack means it's not taut, so you don't have any tension there. And that is where you calculate the moments after that, right? So if you didn't know that, it would have been hard for this one. Yeah, vectors should be fine. Was a bit tricky at first. I was confused about the question because yeah, there was a position vector of the target and the distance of B from the target. So and the important thing here for this one is that it gives you the time of 1 and 9, not at 0. So that is the important point there. You need to be careful, right? So it's like I make the time of 1 becomes the original vector here, like the initial position vector. So that is when I calculate it for time equals 7. I need to make that 6. And if you can see here, I make it 6 here, not 7. Because you kind of like have to subtract 1 from that first in order to substitute to the equation that I made, this one, where time starts from t equals 1. So the initial position vector here can start from any time, but you got to be consistent in your working. That's all, right? And don't forget to subtract the time, basically. This one, yeah, equilibrium. Is there any particular thing I want to stress here? Yeah, not particularly. Yeah, okay. Yes, there is. It's about the friction here. So the F equals mu r that you use all the time is not the actual friction. It's the maximum static friction. If the system is not moving, it's called the maximum static friction. And the system doesn't have to always have that friction active, because imagine if you are putting a box on the ground, and then if you don't apply any force, let's say the ground is rough. If you don't apply any force, it's still without any friction. But if you start pulling, let's say 1 Newton, let's say it's small, it's not enough to make it move, friction will have to be 1. So static friction will have to balance out, if it's the static friction will have to balance out any applied force that is less than the maximum static friction. And now when the applied force is about the same as the static friction, that is when we call limiting equilibrium. So it is about to move. Right? So that's very important there that you need to understand. And here we found out that this one, for this question, the applied force, which is the weight component down the slope here, is not equal, or it's actually less than, looking at the coefficient in front of mg there, is less than maximum static friction. So we say that it remains at rest, not sliding down. Okay. Next one is about connected particles. So yeah, the tricky thing in here is that you need to know that when P moves down, A will move up by the same distance. And when B is having the speed of V, when it's touching the ground, when it's just about to touch the ground, A would be moving up with the same speed. Up by also the same distance. So this is 0.5 already. And as you can see, if you add up the two distances, you get 1 meter already. 1 meter from the ground. But the question asks, how long does it take to be up by 1.06 from the ground? So we have to just calculate the further time, the additional time period that it travels from that 1 meter height by another 0.06 meters. Right? So you got to be able to interpret this question correctly to get the right answer. And that was it. So I hope that was useful. I will see you in the next one. Bye.